Hi, this video is about the physical layer of the Internet model. It is the first and the lowest layer. Following are the objectives of this discussion. First, we will have a short review of the OSI model and the Internet model. The discussion is structured around the Internet model's lowest layer, which is the physical layer. We will then define and explain the physical layer and its role in data communication across networks. We will describe the several functions and protocols of the physical layer. We will list and explain the categories of physical media, the signal types in data transmission, data conversion devices, multiplexing, and transmission modes. Physical layer is also concerned with network topology. So we will mention a little bit about some samples of network topology. To begin, let's review the two widely used but slightly different models of how computers are interconnected and the sets of standards for doing so. These are the OSI model and the Internet model. Now ISO, or short for International Standards Organization, is an international organization for standardization. In 1970s, they created the OSI model or the Open Systems Interconnection Model. It is an ISO standard that covers aspects of network communication. The Internet model is sometimes called as the TCP/IP model because the foundational protocols in the suite are TCP or the Transmission Control Protocol and IP or the Internet Protocol. It is also called sometimes as the DoD model or the Department of Defense model, as it is developed by the Department of Advanced Research Project Agency of U.S. Department of Defense. Because of Internet and its popularity, this model is widely adopted. Here are the layers of the two models. On the left column is the OSI model, and to your right is the Internet model. These two models are sometimes called as the 7-layer and the 5-layer models. But as you can see here, the Internet model only has 4 layers. Why? This is the original Internet model. It has a single layer at the bottom called the network access layer. So later, a different version of the Internet model is used where the network access layer is splitted into two parts, the data link layer and the physical layer. So OSI model has 7 layers and the Internet model only has 5 layers. Another thing to point out is the Internet model collapses the top 3 layers of the OSI model into just one layer called the application layer. In this discussion, we will focus on the model's lowest layer, which is the physical layer. Take note that the communication process entails 2 directions. Going down the stack is what we call encapsulation, and going up the stack is what we call decapsulation. Next to the physical layer is the data link layer. The physical layer is responsible for transmitting the bits through the physical link that make up the data link layer frame. Frames are taken from the data link layer and converted into bits and then into signals depending on the actual physical networking media. It is the physical layer's job to retrieve these individual signals from the media, restore them to their bit representation, and pass the bits off to the data link layer as a complete frame on the receiving device. The data link layer encapsulates the data and gets it ready for the physical layer to transmit the data. The physical layer actually transmits the data over the network and receives it. Here is an encapsulated data moving across the physical layer. When you say protocol or communications protocol, it is the implementation of certain set of functions in a given layer. You should be able to categorize it into one of the 5 layers based on the function that it provides. This means that there could be one or more protocols at each layer. For physical layer, here are a few of the selected protocols by which some of you might have probably heard of already or encountered. We will tackle some of it later. The major responsibility of the physical layer is to transmit the bit stream from one end of the circuit to the other end as reliably and efficiently as possible. When we say circuit, it does not only apply to the wires, cables, and air, but also it includes the electronics at each end as part of the devices the medium connects to. The three fundamental functions of the physical layer are: first, providing the physical components needed for data transmission or the media. Second is data encoding. And third is signaling. Encoding is a method of converting a stream of data bits from higher layers into a predefined code. To mention three from a number of encoding techniques, these are unipolar, bipolar, and Manchester. The unipolar approach uses voltage levels that vary between 0 voltage and a positive value, or between 0 voltage and some negative value. The bipolar technique uses both positive and negative voltages. The Manchester encoding used by Ethernet defines a bit by a mid-bit transition of voltage value. Signaling is the generation of the electrical, optical, or wireless signals that represent the data bits, the ones and zeros of the media. The media may be wired or wireless. We mentioned about the circuit earlier. This could be just the point-to-point type connecting only two network elements, or a multipoint type where many network elements are connected through the same circuit. The physical media can be grouped into two categories: guided media, where transmission flows along a physical guide, and unguided media, where there is no physical boundaries. That is, transmission takes place in the air. Guided media includes twisted pair wires, coaxial cables, and optical fiber cables, whereas unguided media or wireless media includes radio and infrared communications. Transmission of electrical waves over the air is used in wireless media, whereas invisible light waves is used in infrared communications. Copper media, such as the twisted pair wires and the coaxial cables, is the most commonly used network media. It is cabling that uses copper wires to signal data and control bits between network devices. It uses electricity. Advantages of using copper are: it has a high ductility, allowing wires thinner than human hair strands. It is malleable. It can be bent into nearly any form without the threat of breaking, so it is used in devices where very thin wires are needed, such as in earphones. Some disadvantages of using copper wire are: it is susceptible to electromagnetic interference, potentially leading to some devices working improperly, and it does not perform very well when handling exact amount of small electricity charges or the inability to control electrical surges. A fiber optic cable is a network cable that contains strands of glass fibers inside an insulated casing. It uses light to transmit signals. Some advantages of using fiber cabling are: it has greater bandwidth. It is secured as it is highly resistant to tapping, radio frequency interference, and jamming. And there is low attenuation, meaning there is little data loss even over very long distances. Disadvantages of using fiber cabling are: it is costly. The cables, transmitters, and receivers are expensive. It is vulnerable. Optical cables are made of glass, therefore are prone to burn out when too much optical power is used. And it cannot transmit electricity, only data. Wireless communication uses radio frequencies or infrared waves to transmit data between devices on a LAN. Advantages of this are mobility, cost-effectiveness, and adaptability. There are also several disadvantages when using wireless. One is security risk. limited coverage, and slower compared to other forms of media. So we are done with the circuits or the media. Next, we will discuss the data transmission and the types of signals. Data transmission is a process of sending digital or analog data over a communication medium to one or more computing, network, communication, or electronic devices. So as mentioned, the types of signals on the circuits could be analog or digital. In analog transmission, information is translated into electric pulses of varying amplitude. The data are transmitted in continuous wave format such as produced by telephones. In digital transmission, information are sent over physical communications media in the form of digital signals. The data are transmitted as square waves with a clear beginning and ending such as produced by computers. Data need to be converted between analog and digital formats to be transmitted appropriately. To do this, conversion-specific devices are used such as modem and a codec. Here is an example of analog signals carrying analog and digital data. A modem or modulator demodulator is needed to convert digital data into analog form that is suitable for sending it over the circuits using analog transmission. Here is an example of digital signals carrying analog and digital data. A codec or coder-decoder is needed to convert analog data into the digital format that is suitable for sending it over the circuits using digital transmission. Let's discuss multiplexing. The different kinds of media that we have discussed are capable of multiplexing. So, what is multiplexing? Multiplexing is a technique by which different analog and digital streams of transmission can be simultaneously processed over a shared link. This technique requires system hardware called multiplexer or MUX for multiplexing the streams and sending them on a medium, and demultiplexer or DMUX, which takes information from the medium and distributes to different destinations. There are several kinds of multiplexing. In this discussion, we will only mention three. First is the frequency division multiplexing. It is a technique by which the total bandwidth available in a communication medium is divided into a series of non-overlapping frequency bands, each of which is used to carry a separate signal. Second is time division multiplexing. It is a method of transmitting and receiving independent signals over a common signal path by means of synchronized switches at each end of the transmission line so that each signal appears on the line only a fraction of time in an alternating pattern. Third is wavelength division multiplexing. In fiber optic communications, this is a technology which multiplexes a number of optical carrier signals onto a single optical fiber by using different wavelengths of laser light. Other kinds of multiplexing are space division, polarization division, orbital angular momentum, and code division multiplexing. We are done discussing the types and characteristics of the physical media, the types of signal in data transmission, and multiplexing. Let's proceed on the flow of transmission or the transmission modes. The transmission mode is a transferring of data between two devices. The three types of transmission mode are simplex, half duplex, and full duplex. In the simplex type of transmission mode, data can be sent only through one direction. That is, communication is unidirectional. We cannot send a message back to the sender. In the half duplex type of transmission mode, data can be transmitted in both directions on a signal carrier, but not at the same time. In the full duplex type of transmission mode, data can be sent in both directions as it is bidirectional. Data can be sent in both directions simultaneously. We can send as well as we receive the data. Different physical media support the transfer of bits at different speed. Data transfer can be measured through bandwidth, throughput, and goodput. Bandwidth is the information amount that can flow from one place to another in a given amount of time. Throughput is the measure of transfer of bits across the media over a given period of time. It is affected by the amount of traffic, type of traffic, number of networking devices encountered, and as such. Goodput is the measure of the transfer of usable data after protocol overhead traffic has been removed. The network must be designed with utmost care. It is the network's engineer goal to supply the best goodput possible through a high-quality network design. The physical layer is also concerned with the network topology and how the transmission media is to be distributed. Some examples are point-to-point, bus, star, ring, mesh, tree, daisy chain, and hybrid topology. The point-to-point network topology. This topology contains exactly two hosts such as computer, switches, or routers, servers, connected back-to-back using a single piece of cable. Often, the receiving end of one host is connected to sending end of the other and vice versa. The bus network topology. Every workstation is connected to a main cable called the bus. Therefore, in effect, each workstation is directly connected to every other workstation in the network. The ring network topology. The workstations are connected in a closed-loop configuration. Adjacent pairs of workstations are directly connected. Other pairs of workstations are indirectly connected, the data passing through one or more intermediate nodes. The mesh network topology. A host is connected to one or multiple hosts. This topology has hosts in point-to-point connection with every other host, or may also have hosts which are in point-to-point connection to few hosts only. There are two types of mesh topology, the full mesh and the partially mesh. In the full mesh, all hosts have a point-to-point connection to every other host in the network. In the partially mesh, not all hosts have point-to-point connection to every other host. Hosts connect to each other in some arbitrarily fashion. This topology exists where we need to provide reliability to some hosts out of all. The hybrid network topology. This is a network structure whose design contains more than one topology. The star network topology. There is a central computer or server to which all the workstations are directly connected. Every workstation is indirectly connected to every other through the central computer. The tree network topology. It is also known as hierarchical topology. This is the most common form of network topology in use. This topology imitates as extended star topology and inherits properties of bus topology. So being the first layer in the Internet model, the role of physical layer is the transmission of bits between the different devices. Physical layer is concerned with the types of physical media, data transmission, types of signals, data conversion devices, multiplexing, and network topologies. It is important to have a good understanding of this layer as preparations to future problems you may encounter in network communications and to come up with good decisions in designing a high-quality network architecture. So that is all about the physical layer. Thank you for your time.